When a bare finger swipes across a smartphone screen, the device reacts instantly. The glass follows your movement with sub-millimeter precision. But try the same gesture while wearing a thick winter glove or by using the wooden end of a pencil. You get zero response. This selective responsiveness is the defining feature of modern mobile technology. It raises a specific physical question. Why does the glass ignore a pencil or a glove, but acknowledge your skin the moment it gets close? Unlike a mechanical button, a smartphone screen is a rigid, immovable sheet. It doesn't bend, it has no internal springs, and it doesn't move when you apply force. Older, resistive screens, the kind found on early ATMs, actually felt physical pressure. They used two flexible, conductive layers separated by a tiny gap. When you pushed the screen, you mechanically forced those layers to touch and complete a circuit. Because the system only looked for mechanical contact, a credit card, a plastic stylus, or a gloved hand could all apply the necessary force. Modern smartphone glass, however, is entirely rigid. It doesn't rely on the physical deformation of the screen to register a command. If the device isn't feeling the weight of your hand, it's detecting a different physical property entirely, one that is unique to the human body. Beneath that protective cover glass sits a transparent layer of indium tin oxide, or ITO. ITO is used because it combines two properties that rarely coexist in nature. It is highly electrically conductive, yet almost perfectly transparent to visible light. This material is laid down in a precise matrix of crisscrossing rows and columns. These lines function as an X and Y coordinate system, separated by an ultra-thin insulating layer so they never physically touch. This architecture forms the basis of what is known as capacitive touch technology. By embedding this conductive web, the glass is transformed into an active sensor array, constantly monitoring the environment for an electrical disturbance. The device runs an oscillating current through this grid, which projects an invisible electrostatic field just above the surface of the glass. This projected field is what gives the technology its full name, Projected Capacitive Touch, or PCAP. Because the human body is composed largely of water and salt, you are a natural conductor of electricity. When your finger enters that field, its conductivity draws away a tiny amount of electrical charge from the grid. The phone's controller measures this drop in charge at the specific intersection where the disturbance occurred. By calculating this change, known as mutual capacitance, the system pinpoints the location of your finger on the X and Y axes. Wood, plastic, and thick winter gloves are electrical insulators. They block your body's conductivity, which leaves the electrostatic field undisturbed. Because there is no change in the field, the controller never registers a touch. Since the grid is composed of thousands of independent intersections, the controller can track many different points of contact at the same time. This nodal tracking enabled multi-touch gestures, allowing users to zoom, swipe, and rotate objects with multiple fingers simultaneously. This capability reached the mainstream consumer market in 2007, shifting the standard for how humans interact with digital information. Direct manipulation of the interface replaced the need to navigate through tiered menus using physical buttons or directional pads. Because PCAP technology is solid-state and lacks moving parts, it does not suffer from the mechanical wear that eventually degrades resistive screens. This durability, along with high optical transparency, allowed the technology to scale into mission-critical environments, such as the integrated control systems in modern automotive dashboards. The same sensing grids are now standard in high-traffic infrastructure, like airport kiosks, where the system must remain responsive through thousands of daily interactions. If you've ever tried using a capacitive screen in the rain or with gloves, tell us about it in the comments, and subscribe for more technical deep dives. The next time you tap your screen, you aren't just touching glass, you are interacting with